Good morning. So I'll start this second morning of lectures. So last time I started a little bit the connection between what I had been saying and related approaches. I couldn't handle the ODE case. I was about to start stochastic interpolance and then stochastic localization. That's my chapter 4. And I will postpone it here if I have time at the end, because okay, I need to find time. I thought I had 6 hours, so I need to find a little bit of time. So today's program is to make use of the formalism of generative diffusion that we have discussed 2 days ago, and see how it applies in a system which is a very large dimensional system. It's a relevant question because, I mean, in general, you use it for images, you use it for text, etc., which are embedded in extremely large dimension, actually. So the question that I will, as I was saying at the beginning, the idea behind that is that, well, first of all, the whole generative diffusion itself is a physical process. I mean, you degrade with noise and you denoise. It's something which is extremely rooted in physics. And then the large dimensional limit, we know how we know. We have a certain number of methods from statistical physics to handle this limit. And so it's interesting to see how things behave. So the first thing that I want to do now is always start from simple cases. So I will start from an example that I will study at length in quite some detail so that you can understand how it goes. And it's a simple model of statistical physics, which is a Curie-Weiss model. It's a mean field model for ferromagnetism. And the question behind is how the generative diffusion handles the phase transition. How does it recover the various phases, the ferromagnetic phases, etc.? How does all this work? In particular, what happens in the large D limit? So that is what we will do. So what I will describe now is the distribution P0. P0 is my distribution from which I want to sample, etc. So it will be a Curie-Weiss model, but slightly modified. So let me define for you the P0 of the Curie-Weiss as it is written in textbooks. So it is, first of all, the support is variable AI, which are plus or minus 1. And I will have D such variables. I mean, the N of physics has become D when you start to go to machine learning. And the usual P0 Curie-Weiss is just written as e to the beta over 2n sum over I of AI square. Okay, and this is a partition function 2n. Okay, I'm sorry, there will be some mistakes from time to time. Some D will become capital N, but so if you see arriving a capital N, tell me and I will change it to D. So this is a standard measure. You see that it favors the configuration which have a magnetization, which is either positive or negative, actually, but which have a sum of IAI, which is large. While, of course, the entropy, the pure number of configuration, favors the configuration in which the AI are balanced and sum of AI is small, or is over the square root of D, let's say. So there will be this interplay between entropy and energy, and it leads to a phase transition. The one way to write it and to solve actually the problem is to write that as 1 over z and decouple the square by a Gaussian transformation. So I can write it like that. I introduce an auxiliary variable m, and I will write minus beta d over 2 m square, and then I will have a e to the beta m sum over I of ai. So there is probably some so here what I can see is that if I introduce one extra, so I have my variables a1 up to ad, which are easing variables. And then I can introduce one extra variable, so I go from d variable to d plus 1 variable. And this this variable is this variable m, it's a collective variable, and it has a Gaussian measure. Okay. And if you do that, it is the problem becomes relatively simple, because you can introduce the joint probability of the variable m and all the spins. And this joint probability is 1 over z. Z is a generic name for the constant. It's not always the same z. You adapt the z to the formula. So it is just this. So this is a joint probability. From that, first of all, I should say something about m. Why is it called m? Because it's a magnetization. If you look at this formula and you compute the expectation value of m with the measure which is here, you see by whatever, integration by parts, if you want, you see that it is equal to 1 over d sum over I of expectation value of ai. So the expectation value of m is the magnetization. Okay? So if I look at that, I can look at the p0 of m. If I now sum over all the spins, that's very easy, because given m, the spins are independent random variables, and so I find that this is log 2 cosh. And so this is something which is e to the minus d times beta times m squared over 2 minus 1 over beta log cosh beta m. So we can look at, we are interested in this is proportional to, we are interested in the large D limit, and we can look at this potential. This potential, it has a quadratic part, and this also has this is a log cosh. So around m equal to 0, this will go like minus beta m squared over 2. And so the curvature of the potential changes. And if we look at this effective potential, for beta less than 1, we have a potential which is like that. And the optimal is found at m equal to 0. For beta larger than 1, we have a potential which is like this. The potential is at plus or minus m star. And m star is the minimum of this function, so we find the celebrated formula that m star is equal to tanh of beta m star, which has a non-trivial pair of solutions plus or minus m star when beta is larger than 1. Okay, I go fast, but I think it's okay. Yes, you have been teaching that, all of you. So good. So that is the thing. So we know all that. We have a large deviation principle and a rate function for the magnetization. And the point that I want to insist upon is that given the magnetization, the spins are independent. They are uncorrelated. So basically, one way of looking at the Curie-Weiss model is to say I could look at I could first draw M, could look at the following distribution. I could look at P0 of M, and then P0 of the AI given M. Okay. And if I do that, what I see is that if I am in the low temperature phase, basically the distribution of m will be very peaked around m star or minus m star with a width of order 1 over square root of n. Okay, so it will fluctuate very little, it concentrates. And given the m, you have the ai, which are independent Ising random variable in an external field which is beta m. So this, we could handle this problem very easily, but I will introduce a slightly simpler version of the Curie-Weiss model, and because just it will be a bit easier, a bit faster to write. So my simplified, slightly simplified, it has exactly the same physics. My simplified Curie-Weiss will be, okay, I write it as CW, but then I will drop that, and it will be P0 of A, which I write in general like that. I will write it as W plus product over I e to the beta m star AI over 2 cosh beta m star plus W minus product over I e to the minus beta m star AI over 2 cosh beta m star. Okay, so what did I do? I did two things. On the one hand, I substituted my P0 of m, which you remember it was a large deviation thing, etc. I substituted it by something that is just delta of m minus m star with a weight W plus W minus delta of m plus m star. Okay, so I had exponential minus n times this function, minus d times this function, and I substituted by just 2 Dirac. Okay, and then I put weights W plus and W minus. That is, I slightly shift the bottom of the well in order to allow for an asymmetry. Okay. And here m star should be thought of my initial variable. It's the spontaneous magnetization of the Curie-Weiss. So it is equal to tanh beta m star. So this is just how you go from the standard Curie-Weiss to the slightly modified one. It's a very mild variation. Okay, it is basically, what is it really? It is a bimodal distribution. Bimodal distribution with two modes, let's say, which are related to phases which have magnetization m star or minus m star. And in each mode, you have independent spins with an external field which points in the direction of m star. Okay, this is the essence of what Curie-Weiss is. I did not do anything. Okay, so now, so this was the definition of the model. Maybe I have to copy it here. The dots means the right normalization. And now what we will do is study what happens to generative diffusion and we study generative diffusion with this model as initial condition. So that is, we draw some configuration of the Curie-Weiss. We do the forward diffusion, we do the backward. And what I will do, it's a very it's a really simplest exercise as possible. I assume that we know the perfect score. Okay, so we use the perfect score. So at the moment, I'm far from applications. I mean, I don't play the game of generating for you samples of Curie Weiss and then doing the score from that, etc., etc. But you can do it, and you can see how. But now I want to do the theoretical analysis. What happens if you have the perfect score? So what we have is the following. First of all, I need to write what is the joint probability of x at time t, and A, which is the initial condition. And this, you remember that it is P0 of A times the product of I e to the minus xi minus ai e to the minus t squared over 2 delta t. Okay, this is what we had derived. That is just Ornstein-Uhlenbeck. We start from A, we evolve at time t, and at time t we have x, which has a mean which is a e to the minus t, and with the delta square root of delta t. You remember, this is my basic drawing. This is the mean for each component. Does like that, a little bit of noise, more noise, and then here I have noise of width 1. Okay, that's what is written. That's the probability distribution which is here. I substitute P0 of A. I have two modes. I have the W plus and the W minus. So it means that this will be equal to W plus PT plus of X and A plus W minus PT minus of X and A. And I can write what is PT plus or minus. So that is, I remind you, the joint probability distribution of the initial variable here and a variable x taken at time t. Okay, and so this you can see it as the joint probability distribution when A has been sampled from this guy here. So it is in one of the wells of the one with positive magnetization. And so what is it? Well, I just have to substitute. I just need to add this measure which is here. And so this I can write as follows. I will write it as product over I. I will get out xi squared plus ai squared, which is 1 e to the minus 2t. Okay, these are the squares. And then I have a product over I e to the plus or minus beta m star plus xi e to the minus t over delta t ai. So what did I do here? I picked up for each I have the term of the measure which comes from the initial measure, e to the plus or minus beta m star ai, which is here. And then I have the term which is a cross product of this guy. You remember that the measurement x at time t, if you look at it from the point of view of A, it looks like a pinning field. It looks like an external field. Here we see it precisely. It's just an external magnetic field proportional to xi. Okay. Sorry? I have not defined delta t. I had defined delta t, so everybody remembers it, but not quite. Delta t is 1 minus e to the minus 2t. This was what we derived from Ornstein-Uhlenbeck. Thank you. Good to recall that. Yes, delta t, the thing that you have to remember about delta t is the width of the noise. So when you are at very small time, the noise is delta t, you see it's linear in time, it's very small. So x is very strongly correlated with A. And then when we are at large time, you have a noise which has a width which goes to 1, because that's my Ornstein-Uhlenbeck. It thermalizes. So now let me look. So now you remember that in order to do generative diffusion, I will need the score. And in order to compute the score, you remember that there are trivial part of the score proportional to SI proportional to XI, so we will compute that. But then the non-trivial part of the score is the expectation value of AI conditioned to X and T. Okay. So this means that I need to compute the conditional probability of A given X and this conditional probability, I rewrite it as follows. So first of all these terms will disappear because they are not independent. They are not dependent on A. So I will get the following. Let me write it. W plus e to the beta m star plus xi e to the minus t over delta t ai product over I plus W minus times the product over I of the same thing with just a minus beta m star, and the rest is unchanged. And then there will be a normalization. And the normalization, it is an easing measure, so the normalization is obtained by taking the sum of AI of the numerator. So it is just W plus product over I of 2 cosh beta m star plus xi e to the minus t over delta t plus W minus product over I of 2 cosh minus beta m star plus xi e to the minus t over delta t. Sorry, it's slightly long to write on the board, but it's a very straightforward computation. So you see that, well, you can read it now. Now let us read that. What does it mean? It means that really we have we still see the trace. So this is a constant. This is normalization constant. Depends on x. It's important because it depends on x. But then in the numerator, what we have is that we have the two modes. And in each mode, the AI are independent random variables. Okay? But it's a superposition of the two modes. So from that, you can do the exact computation of what is the expectation value of AI. And I will not do it. I will give you the result. It's it takes a page, which means 3 blackboards, and it's a bit boring, but it's a very simple exercise. I mean, you have the measure, you do it, and so what you find is that AI conditioned to X, so you take just the expectation value of one AI. Okay, so you see that when I condition on AI, it means that instead of having, when I do the expectation value of AI, it means that for that index AI0, let's say, for that index I0, instead of a cosh, I will have a cinch. Okay, and I have to now and then I organize the cinch and the conch and the tanch and the thing, and that's and it gives this. It gives the following. Already writing the result will take me half a blackboard. So AI conditioned to X is equal to Okay, that's the result. Well, oh no, I need to tell you what is Q plus and minus. Okay, so AI, expectation value of AI, it depends on the spin index. It depends on the index I, and it depends on each explicitly through xi, which appears here. And not so surprisingly, you see appearing the tangent of xi, because xi was like a magnetic field pointing in the direction. So it's not a big surprise that there is this. But it also depends on all the other x variables. It depends through this. This is x is a collection of all the variables. So it depends on where you are in the space. And this is the function that you get. It's a function that is a product of factors in each direction. You have to remember that this point here is a spin configuration. It's a configuration of d spin. It's a point on the unit hypercube in d dimension. So it's one of the 2 to the d possible configuration of the spin. As soon as I go away from there, as soon as I start my diffusion, I go to r to the d. Okay, so I start from in d-dimensional space, I start from a point in the hypercube, and then I start to diffuse. I leave the hypercube. I go from easing variables just here, and I start to have real variables. Okay, and my score function is defined everywhere in space, not only on the hypercube. So this is how it goes. It goes like it depends on all the coordinates, but only through this kind of collective function. And so this is the simplicity of this model. That's why I wanted to show you the result, because it's a mean field model, and so one can write everything explicitly. I mean, one can arrive at the right result. And so now that we have that, we can start to study what happens. So we need to find the score function. The score function, you remember that if I look at the backward Langevin, it was written like dxi d tau is equal to xi plus twice the score plus some delta correlated noise. And this is using the backward diffusion starting from a time tf, and I measure now the time like tau, and the original time is t. So I have tau, which is tf minus t. And I'm moving like that, increasing tau. So if I look at the formula, the 3D formula for the score, I plug in all that. What I will have is Si of x and tau is equal to minus xi over the delta, the famous delta tf minus tau. Keep that in mind. And then Okay, so this is our Langevin equation. Langevin equation, it has a force. You remember this was a quadratic, not well, but a quadratic repulsive field. And this is the score which comes from that, and that is proportional to this function of x. Okay. It's not, if you think about it, it's relatively simple. But let us try to understand what happens in various regimes of time. And so what I will do now is study this system in the limit of large time. And we will see a phenomenon that we have called speciation. I should say that this is work we did with Giulio, which appeared a few months ago. So let me look at what happens at large times. So I take TF, which is very large, and so T will be very large. Okay. And if T is very large, I can start to simplify a little bit my score. What I want to understand is exactly, I want to understand how is this force field. You know, I have this is an effective force. It's a driving force for my Langevin. I want to understand its structure. And so at large time, when I start from over there, what happens? How is the score? And you see that when T is very large, well, xj is over the 1 because I start from some xj which is just a Gaussian. So xj and delta t goes to 1. So xj e to the minus t over delta t is much smaller than 1. So we can expand things, and we find that our two functions, these two functions are the one that makes life a little bit complicated. If I did not have this function, I would have a score which depends only on xi. It would be a one-dimensional problem, and I am home. Okay, so I want to understand exactly what happens to this q plus or minus of x. And what I find is that this is equal to product of a j1 plus or minus m star xj e to the minus t over delta t, and this is equal to exponential of plus or minus m star e to the minus t over delta t, sum over j of xj. So this is interesting because it tells us that this global function that depends on the space, etc., in a slightly complicated way, if I look at it at large time, it's a function that depends only on sum over j of xj. Okay. So it's not surprising. I mean, we know from general principles, we know that we are doing a backward diffusion on the problem with the exact score. It has to give back the original P0. And the original P0, it had two modes which are conditioned by the magnetization. So not surprisingly, the score, the 2D formula for the score, at least in the first regime, in the very long time regime, what you see is that it depends on the position of space through the magnetization. And it's a unique collective variable. So basically when you put that in this formula here, you see that AI, and therefore my force field, it depends on two things. It depends on xi, and it depends on the total magnetization. So I can introduce a collective variable, which is a total magnetization, and then the things will decouple. Exactly like we had at the equilibrium measure. Yes, Antoine? You mean large time, you use scaling with 0? No, here I need, we will see that later on. But at the moment, what I am doing, the only assumption that I did, I should say, this is exact. Okay, just standard calculus. And this is exact, provided this is correct. And so xj is over the 1, so it's just large time. So when you use this approximation for the score, what you get okay, I need to do a little bit of gymnastics on this formula. Here you see that at large time, this is just tanh beta m star. So this will be equal, tanh beta m star is also m star. This is minus m star. And then you have the q plus and the minus are these exponential which are here. So basically what you get, putting all the factors together, is that ai x at time t is when, as soon as e to the minus t is much less than 1, you get something which is m star w plus e to the m star e to the minus t over delta t sum of xj minus w minus e to the minus m star e to the minus t over delta t sum of xj over w plus e to the same thing plus w minus e to the minus same thing. Okay, you understand what I mean. I mean, I have take this piece, copy it here, take this piece, copy it there. Okay? Well. Can I write here? Yes. Thank you, organizers. They are not very happy, but so I use that. I use the score which is here. I put it in my Langevin, and what do I get? I get that dxi d tau is equal to 1 minus 2 over delta t xi plus 2 m star e to the minus t over delta t tanh of m star e to the minus t over delta t sum of xj plus eta I of tau. And here I have taken the simplest case where w plus equal w minus equal 1/2. So symmetric. The problem of symmetry is interesting in itself, but okay, the blackboard is too short. So this is what we get. It's just substituting in the formulas. And so you see exactly what I was saying before, that we have, for each variable xi, we have a Langevin equation which depends on the other variables only through the sum of xj. Okay? And it depends on xi linearly. So this means that I can do the sum over I of these formulas, and I will have an evolution of equation for the sum of xj. So that's what I will do now. Let me introduce a variable mu, which I normalize like that, 1 over square root of d, sum over I of xi. So that is not exactly the magnetization. It is a magnetization in units 1 over square root of d, which means that, you remember I was at large time here. I am at large time. At large time I have xi, I have to imagine them as they are basically sampled from IID Gaussians. So the sum of xi is over the square root of d times the normalized Gaussian. So the natural scale at large time is 1 over square root of d sum of xi. This is my, let's say, my fluctuating magnetization. Of course, this guy, I hope that at large time of the background process, at small t, it will go to something over the plus or minus square root of d. because magnetization must develop the extensive, that's the phenomenon of the phase transition. But let's look at that. I can add all the formulas which are here, sum over I, and I get an equation for mu. And my equation for mu is the following. I get d mu d tau is equal to, I use that at large time delta is nearly equal to 1, so it is minus mu plus 2 m star square root of d e to the minus t tanh of mu e to the minus t square root of d. So this means that my collective variable, which is the global magnetization in the proper scale of large time, it evolves autonomously in its single Langevin equation with an effective force. And this effective force, this is minus the gradient of minus, well, in this case it's just one dimension, minus d mu of an effective potential Vt of mu. And I can write what is this potential. I find that sorry, I really need to keep that for later. So the effective potential, Vt of mu, is equal to mu squared over 2, which gives me this part of the force here, like Ornstein-Uhlenbeck standard, plus something which is log cosh of mu e to the minus t square root of d. And I need probably a factor minus 2, and I need I had an m star somewhere. I had an m star here. And so I need an m star here. Okay. So what is this effective potential? Well, you see that the shape of this effective potential, so this is just a quadratic well. And this part here, it is a function which is more done like that. It's a log cosh, so around the origin it is a quadratic function, and at large argument it is linear, and it is negative. So the thing that will depend, it will depend a lot of what happens, what is the value of this parameter here. So I see appearing here a natural time, which is the time when e to the minus t square root of d is over the 1. Okay. So if I draw the potential various times, I will find the following. If I am at very large time, it means square root of d e to the minus t much larger than 1. Then my potential, the effective potential, is just quadratic around the origin. Okay. Now, much with a very large time, much smaller than 1. And if, on the contrary, square root of d e to the minus t is much larger than 1, then the log cosh becomes an absolute value of mu. And what I have is a potential which is like this. At large argument, it looks like a Gaussian, but at the origin, there is the linear part which comes from the log cosh. And so it develops something which is like that. Beta, this beta here? Yeah. No. Okay, you have to do all the algebra. You use you develop you expand the tanh as tanh A plus B is tanh A plus tanh B over 1 plus tanh A tanh B. Okay. Yes, but this is tanh beta M star. You see, wherever you have a tanh beta M star, it's M star. That's where the beta disappeared. Okay, this is a tanh beta M star. This is a tanh of this thing here, which I linearize, and I use this identity. Is it okay? Yeah. So now you see that the bottom of this well is at m star square root of d e to the minus t, and the depth of the well is also somewhere around that. It will also scale with d. So what will happen, so now you have to imagine your backward flow. It's a backward flow in a time-dependent potential. But I find it slightly easier to visualize the potential rather than the force. Okay? So if you have the potential, you see that the initial backward flow is just a standard Brownian motion, Ornstein-Uhlenbeck motion. And then after some critical time, you start to develop this cusp. And then at some moment when really square root of d e to the minus t is much larger than 1, then you have a well with a very large barrier. You have two wells with very large barriers. So depending on your trajectory, what you will find is that you have the backward trajectory. Maybe I write it there so that it is immortalized on the screen. I have my backward trajectory. I start at this very large time, so it is just in the Ornstein-Uhlenbeck fluctuation. And then at some point here, I will have what I call the speciation time. And the speciation time means that I start to develop this cusp. And when I have well below this time, in the scale of t or at larger tau, then what happens is I pick up one of the wells and I evolve, or I pick up the other of the well and I evolve. And if I am here, if my trajectory by case has fallen in this part of the phase space, it will never come back. Okay? So this is what we call the speciation time. The speciation time is defined by square root of d e to the minus t speciation is equal to 1. So it is 1/2 of log of the dimension. And the speciation time is really when you have the trajectory that commit to one part of one of the wells. And so you will have two kinds of trajectories, and this will happen starting from initial random condition completely. So you will have the one that go down, the one that go up, and initially you cannot say anything, but then once you have committed, you are either here or there, and you don't mix. So this is what we call, this is a very generic phenomenon. This is what we call regime 1, and this is what we call regime 2. And in between is the speciation time. They are separated by a speciation time. And the speciation time is well defined on the scale of log d. It's on the scale of, when log d goes to infinity, the speciation time is 1/2 in scale of log d. Okay? But of course, if you then you have some finite, depending on what is the criterion that you take for speciation, around 1/2 of log d, you can, depending on your criterion, you will have more or less some small fluctuations around it. Yes, yes. The cusp is the same cusp. Yeah, but, I mean, yeah, Burger's equation is, I mean, Yes. The joint distribution P of A and X, which is P0 of A, e to the minus x minus a e to the minus t squared over 2 delta t, this is exactly what happens in Burger's equation. That is, you have, if you write it in terms of, if you write this as exponential minus Vf, certain V of A, and what you have is this smoothing exactly. And the thing which is nice is that the thing that I like in the generative diffusion is that you have this the time of the inverse diffusion. It acts like a length, like a length scale. Like we are doing some kind of renormalization in some sense. I mean, we are looking at very large time. Here, we are looking at really large scales. Delta t is large, and you have to remember that a has also been shrunk by the factor e to the minus t. And gradually we refine. And we will see that the first refinement in Curie-Weiss is a refinement in which we split into two clusters. And then we will see some further refinement that appear later on. But this is important because it tells you that really the time acts like a scale parameter by, if you want to look at a stat-phys problem. I mean, the correspondence with RG is here. So how you can test this idea of the speciation? You can test the idea of the speciation as follows. There are two numerical methods that have been developed to do that. The speciation time? No, there is, but it's a okay. I think that if you do it with all factors, I'm not sure if I have it. As far as I remember, there is a m star here or something like that. But in the scale of 1/2, if you imagine log d is large, then that's a correction, let's say. It's part of the arbitrariness of the definition of the speciation. Okay. Yes?
Is there any dependence on the temperature of the nodes that you use to go back in time? I mean, if you put the nodes, because you fix,
no? Here, from the beginning, both in the forward and in the backward, I have taken my noise, which is delta correlated with temperature 1. No, I think it's just it rescales things. I mean, it would just I could have kept. It's just that I was lazy. I could have kept this temperature in all the formulas. It would not. It will change the time scales. It will change the time scales. Yes.
But you could decide that you go towards, another.
Yes.
Something which is scaled differently, where the variance could be d, for example.
Yes.
That changes.
Okay. Well, it's a pity that I could not do my chapter 4 because I wanted to discuss that in the things which are related, and the things which are related are this change of scale of time or of noise. I mean, I have decided to keep one thing so that people can try to follow, which is just the standard Ornstein-Uhlenbeck at temperature 1, because but you can do very different. For instance, you see that everything that I said, you could redo it with very different schedules. You could do it with a schedule which is like that. Imagine that I have my Curie-Weiss process, and this is my two wells. Okay, I don't know how to write it. They are in d dimensions, so they are okay. I have my wells here. These are configurations of hypercubes which have sum of AI which is nm star, and these are minus nm star, and then I look at time t. So what I did here is this Ornstein-Uhlenbeck. But another thing that I could do is just not put the confining wall, not put the confinement, not put the Ornstein-Uhlenbeck, just do standard Brownian motion. Then what happens is that you have all your trajectories, you add noise, and you add noise, and so you go to large time TF, and you have a big Gaussian, very broad, well, very broad, square root of TF. And but then the point is that you forget the initial condition. And so you can, everything that I did, you could do it with this. That's a variance expanding case. It works the same, I mean, mathematically. Then the subtle things, some subtle things happen that the spatiation time, etc., they will depend on the schedule. They will depend on what you do. For instance, well, one thing that we started working on and discussing and working on with Eric is you have schedules in which you do the diffusion, instead of doing it from 0 to TF very large, you rescale things so that the final time is 1. Okay, so you write e to the minus 2t, you write it as a t hat, let's say, or whatever, or maybe write that as 1 minus t hat. Yes. So that t going to infinity is t hat going to 1. Okay. And that's a very valid schedule. You can rewrite. You remember 2 days ago I told you how to rescale the time in the Langevin equation. So you can write everything with such a new definition of time. But then, if you do that, the speciation time will appear at a time. So the final time is t hat equal 1. But then the speciation time will appear at t hat of order very close to 1. Because, okay. So, sorry, I cannot, I keep to my simple thing so that because there are too many things to say. Where was I? I don't know. Yes?
In this perspective, where you know perfectly the score, the backward equation is perfectly equivalent to the forward equation.
Yes.
So this is the kind of where you just in the forward direction, you lose the memory of the initial condition.
Absolutely. And that's exactly what I wanted to say. Thank you. I offer you a coffee at the break. So, yeah, I wanted to say how you measure that numerically. Okay, so the idea, as I told you, is to use these simple models in order to find, to understand what happens, and then you want to test it on more realistic models. I mean, you're not interested in generated configurations of Curie-Weiss. Come on, you know how to do that. That's very easy. So, but you want to understand the mechanism. And so, once you have these speciation things in mind, how you measure that? There are two ways to measuring speciation. Two ways which are equivalent, basically. The first method was is a U-turn that was found by Misha Chertkov and Bijou. And the second method is cloning that we have been using with Giulio, Bonner, De Bortoli, and myself. And so the U-turn is the following. The U-turn is you start from a configuration which is sampled according to P0. You let it evolve, but you don't go to very large time. You stop at a certain time TU. You arrive at a certain configuration at this time TU, and then you go backward. And then you can have two things. Either you go backward to something which is in the same cluster, so that's my cluster of plus m magnetization, and this is my cluster of minus m configuration. So depending on TU, Well, maybe the backward diffusion will take you somewhere in the cluster, in the same cluster. Or maybe, if TU is long enough, maybe you will go back here. So you can look at, depending on TU, you can look at the probability that the, so this is called a U-turn because you drive up to TU, switch back, go back from the configuration you had reached. Okay. And you can look at the probability that the configuration obtained at time 0 after a U-turn at time TU is in the same cluster or not. And this probability, if TU is very, very small, obviously it is equal to 1. And if TU is large, it will go to 1/2. Okay. And you can look at that and look at the speciation time. Another thing that, an alternative thing that we have been using is something that we call the cloning. So in the cloning, you do something slightly different. You start from large time, TF, generate your configuration, and at some point here, you take the point where you have arrived, so that will be the time of cloning. And from this configuration, you generate two clones, X1 and X2. They have the same value here, but they have different noise. And you see if they tend to arrive to the same cluster or to two different clusters. Okay. And you can look, basically you have the same kind of curve. You look at the probability that the two clones arrive in the same cluster as function of T of T cloning, and you will find the same kind of curve. The detail of the curve depends on the process, but the whole idea is exactly this one, and it's the one that is characterized here. And that you see the physics is there. The physics is from the cusp and the existence of the double well, and the double well which in the large dimensional limit you cannot hop. So this tells you that once you are beyond, when you have time smaller than the speciation time, you are committed to one of the wells, and you know that you will end in this same well. Yes.
So instead of starting at T equals TF, you can actually start just a bit without the speciation time.
Yes, absolutely. Oh, yes, that's one of the practical consequences, is that really this is a crucial time, let's say. This is a crucial time, and you should handle that. It's the moment, in particular, if you have the two wells at the moment, because the trajectories, they commit now to one of the two wells, the relative weights, they will be decided here. Once you have passed that, you will not change the number of trajectories which are up or down. So the weights you generate. So this thing here should be handled with care. It's a moment in which you should have a good score function to do that.
Do you think really people use this in practical applications, in sampling more efficiently?
Well, we will show you data next month or whatever. When I thought Tony was here, but okay. Well, Tony Bonner is doing the simulations at the moment. So, okay. So then maybe one last point that I want to discuss using still my Curie Weiss is what happens in regime 2. So regime 2 is when T is less than speciation. So I know that I have my P of x has really, it means that my P of x has two well-separated modes. I mean, all this is just the structure of the probability distribution in large dimension. And you gradually smooth it. If you smooth it too much, you lose the existence of the two wells. If you smooth it just barely at the limit, you have the two well barely separated, that's the speciation time, and then they get well separated. So what happens when you are in this regime 2 where they separated? Well, what we have now is that we have two types of backward trajectories. So we have the backward trajectory which go up and the one which go down. Okay, imagine that I am at a time like this. And so if I look at the trajectories which are in this cluster here, they don't care at all about what happens in this other cluster. Okay? So let us look at the expectation value of AI when x now is in the region in which sum of xj is positive. Well, we have, I can look at what is q plus or minus of x. And this is exponential, sum over j equal 1 to d of log 1 plus or minus m star tanh of xj e to the minus t over delta t. So what is this guy? Now what I have to assume, I assume that xj, it corresponds to this, to this cluster. It's a cluster that I call the cluster plus, and this is a cluster minus. In my trajectories here, they define a certain distribution, an effective p plus of t and p minus of t, and they are separated. So my x has been generated according to p plus. You remember at the very beginning, I had P0, it had a P0 plus and a P0 minus, and I said P at time t, it is a superposition of a PT plus, which is obtained from this, convoluting with the Gaussian, and a PT minus, which is obtained from that, convoluted with the Gaussian. So what is the PT plus of x? PT plus of x is just a factorized distribution. It's product over I of rho t plus of xi and rho t plus of xi. I can write it as the sum over ai, which is plus or minus 1, e to the beta m star ai over 2 cosh beta m star times the Gaussian. So this means that condition to the fact that x is in the cluster plus, which is a valid hypothesis because I know that my clusters are separated. Condition to this fact, I know that the xi, they are independent. They are independent random variables. Okay? The xi are independent random variables, IID, so it means that q plus of x, it means that this sum, it goes to a limit which is its mean. So really, q plus or minus of x, it goes at large d to exponential d times integral dx rho t plus of x log of 1 plus or minus m star tanh x e to the minus t over delta t. Now, it is easy to see that here in the measure on x, I have a bias. I have a bias because the AI equal +1 is favored by my well. So AI equal +1 has more weight. So it means that I will have more weight on xi positive than on xi negative. And using that, you can see that this expression here, when it has the plus sign, it is larger than when it has the minus sign. So it means that really q plus of x, let me write it like that, q minus of x over q plus of x goes to 0 when d goes to infinity. It self-averages, it concentrates, and the q plus dominates. And it dominates exponentially. It is exponentially larger. So if it is exponentially larger, it means that really, when I am here, when I compute the score, I can forget about these guys here. So it means that expectation value of AI is tanh beta m star plus xi to the minus t over delta t. The spins become independent, they have independent trajectory, and they have a score which is exactly the score of if you had done the diffusion for one single Ising variable initially, well, that would be the score that you would get. So this will take you back to an initial variable which are uncorrelated, but with a bias, so that the expectation value of AI is m star. So it does exactly what you wanted. It reconstructs the well plus magnetization of the initial distribution. So you see two things. Why did I want to do that? I wanted to do that to well, it turns out that the Curie-Weiss, you can do everything. So you can really study in all detail. So looking at the perfect score, on the one hand, you first find the regime 1, very long time, and then you see at some point that there is an instability and development of this double well. That's the speciation. And then when you are here, you can see from the formula that what happens is that you have exponential dominance of one of the wells on the other one. And so the spins, the variables become independent, completely independent in all the dimensions. And you reconstruct an Ising measure. Still not completely trivial. You can do the same thing. It's easier to do it in a case in which a superposition of Gaussian, for instance. Superposition of Gaussian, it's an exercise that I will not do, but you could do it. Everything can be done. But what I like here is that you see the simplification that appears after the speciation. That is, the score here does not care at all about what is happening in all this other region of space. So that is a good lesson also for what if you want to build approximate values of the score, which is another chapter, let's say. But it's still not completely trivial. You know, if you would take just a linear function, you remember I was saying yesterday, 2 days ago, I was telling you what happens if you take a linear score. That in the end, that's the simplest thing you can do. Well, if you take a linear score, you get a Gaussian. So AI would be independent Gaussians. It's not an Ising variable. It's not good. Okay. So these details of the score matter in the sense that you need to reproduce the correct measure at the initial time. But still a lot of simplification had taken place after you have done the speciation.
Can you just say again how we got the Ising measure?
Yes. Yes. So I get that from this formula here, I get that the expectation value of AI conditioned to x is equal to tanh of beta m star plus xi e to the minus t over delta t. And then if I plug that into my usual formula for the score, I find that Si of x and t is equal to minus xi over delta t plus the tanh, which I can write as the derivative of the log cosh. And you can check that this is the backward if you had a single spin xi and you had sampled it from e to the beta ma e to the minus x minus a e to the minus t squared, this convolution here. Okay, so you have a bias, you take with larger probability a equal to +1, and then you put a Gaussian around a e to the minus t. Well, you find that it is exactly the score that you would get for this single spin. If you basically, if you say compute the expectation value of ai conditioned to x with this measure, you find this here. Okay, so you find that it is the score of independent spins that bring you back exactly where you want.
Maybe it's worth pointing out that there's something special about this model, which is that since the measure you start from is supposed on a discrete set, like this score actually becomes singular at t equals 0, so that it crystallizes.
Yes, yes. The whole, yes. As I was saying, the measure is the hypercube when you are just times 0 here. But as soon as you have an infinitesimal time, you are in R to the d. But of course, this 1 over delta t goes to 0 at t going to 0. And so the well will be very, very sharp when you are at t close to 0. And very, very sharp, it will take you back to the Ising measure. Simulate it. It's very easy to simulate. I mean, it's a few lines of things, and you can simulate the backward flow, everything. I mean, it's just, and it works very well. I mean, it worked very. I did not do. I mean, I'm sorry because I cannot. I mean, there is a lot of math behind of people trying to control what happens with the discretization, for instance. I mean, when you do the practical implementation of that, you have two main things. You have the score, but here I have supposed that I know the ideal score, so I want to simulate the ideal. The only thing that remains is the discretization of time. Okay, and so you have to really be able to control what is the error that you make when you have a finite delta t. But okay, that's something that I have not at all addressed in these lectures, but there is quite some literature on that. Let me very rapidly, because I have said quite a lot on speciation, let me generalize a little bit the speciation. It's okay if I, at what time I'm supposed to stop? So I have 10 minutes. So 10 minutes is good for doing the chapter 6. So speciation is a phenomenon that you can look at. So what is the phenomenon? I have already told you. That is, I have told it to you on the Curie-Weiss model, but you can look at it on other models. You can take your favorite database. You take the NIST, the 0s and the 5, and you have two clusters, and you want to know at what time you are committed to one cluster or not. And you can program the U-turn or you can program the cloning, and you will find a speciation transition. Of course, when I say speciation transition, in all kinds of data, you will have several of them, because you will have, in general, there are not, it's just Curie Weiss, which has only two clusters, but in general, in each cluster, there are subclusters, etc., etc. So probably you will have several phase transition. So numerically, I have told you about the two methods. Maybe in the end, I will show a few pictures if we have time. And then let me propose to you a generic approach which is related to a kind of Landau stability analysis, Landau type stability. So it all relies on the following. I mean, the speciation is completely related to the structure of Pt of x. Okay, what is the probability density of x at time t? And so I remind you that general formula is that you generate data from P0 and you make a Gaussian convolution and so what you find is that this is exponential minus x squared over delta t plus g of x, and g of x is the log of the integral over the initial data p0 of a with a measure which is slightly modified. It has a term a squared e to the minus 2t over delta t, and it has a term in e to the minus t over delta t x dot a. So this is like what I call the tilted measure. You remember there is always this interesting way of looking at the problem, which is what I am doing. I can see it as part of denoising. I have measured x at time t. I want to understand what is a given the one that I have measured. Okay, and when my t goes to 0, evolving in the backward process, I have more and more information. Okay? That's the principle of stochastic localization. And so what you look at is how the measure which is here evolves when you do the backward process. And what you see is that there is an effective measure. It is a measure of a condition to x. It is P0 of a. And then there is some Gaussian rescaling. And then x acts like an external field, x dot a. X tilts the measure on a. And g of x is like the free energy of the tilted measure. Oh, but the free energy of a tilted measure is the tilted measure. You can also look at it as okay, imagine that I have defined a P0 renormalized, which includes the Gaussian part, which is here. But the important point is the x-dependent part. The x-dependent part, it's for physicists with field theory or whatever, that's an external field that you have applied to the variable a. It's a linear coupling. But for probabilities, it's also what you will use as a generating function. This, you have an effective probability distribution. So this I call P effective of A. And what I have is a measure which is P effective of A times e to the x dot A with some rescaling which does not matter. But this, we know, if I have P effective of A in general e to the HA, this, by derivation, it generates the moment of the P effective. And if I take the log and I take derivative with respect to H, it generates the connected moments. It's a generating functional for connected moments. Okay, so that is exactly what we are having here. G of x is the one for the generating function for connected moments, and so what you can do is just a perturbative expansion. If you are interested in speciation, it means you are interested in large time. It means that you have a small field. If you have a small field, you can expand in powers of e to the minus t, and it gives you the usual expansion of connected moments. So what you find is that g of x is equal to e to the minus t over delta t sum over I of xi expectation value of ai with the effective measure plus 1/2 e to the minus 2t over delta t sum over ij cij xi xj, and cij is ai aj connected correlation functions. But now you can look at this effective potential here. This effective potential, it is so you have an effective potential V of x at time t, which is at time is large, so delta t is nearly equal to 1, so that is x squared over 2. And then I have a linear part, and then I have a quadratic part, which is just 1/2 e to the minus 2t cij xi xj. So at large time, my potential is basically a quadratic function, and it is governed by a matrix, and the matrix is the identity minus e to the minus 2t times c. So what you expect is that this matrix, it can, of course, it evolves in time because of the e to the minus 2t, which is here, and this is a correlation function of the initial measure. And so what you expect is that there will be a change of regime at the moment in which one of the eigenvalues of m, corresponding to the largest eigenvalue of c, when the largest eigenvalue of c is equal to e to the 2t, then you have a change of curvature. Okay. When t is very large, this is the identity, you have a quadratic well, and at some moment you have an instability. Yes, that's. But at long time, you can check that this e to the minus 2t is irrelevant. So in fact, that should be the effective measure. But if you are interested in the instability at long time, then what happens is, you can take. And so this tells you something which is a general recipe. You can look at, because this correlation, you can look at it. So far, I have assumed that I know the exact measure P0. But then you can look at it on a database. You can look at the empirical correlation function of the data on the database. And so this tells you, so a more generic way of looking, let's say, at the speciation time, it tells you, well, the speciation time, it should be related to the moment in which the largest eigenvalue of the empirical correlation times e to the minus 2t is equal to 1.
This is a bit of a surprising result because, as you said before,
Absolutely. That will be the first one. The first one you will see like that. And even that, I want to qualify it because I think it's not universal. I think it's true. Okay, let me qualify it. But first, what you say. First, in realistic data sets, you don't have just a structure in two clusters. You also have clusters with subclusters, etc., etc. But so what I say is that the first one, you can see like an instability of the curvature. Okay. Then there is a more general approach, and it's not necessarily always the case that you can see the things at the level of the instability of a potential. That's the case in which there is symmetry breaking, and the symmetry breaking you can see it this way. But there are more general cases. I mean, here, what is happening is that okay. Can I do it or not? No. Okay, I will answer this question to you privately, because if I start to do it now, I will not. And so I think it's a good time to stop. Yes, let's have a coffee.